velocity triangles. Something you have to know about the velocity triangles. Velocity triangles are only drawn for moving beams. Okay? We don't draw velocity triangles for fixed beams. We only draw velocity triangles for moving beams. What is meant, or what will be velocity triangles? Definitely there will be an absolute fluid velocity. Here we denote it by CA. Now this velocity is the velocity as seen by, this is seen by an observer who is fixed to the ground. That is a stationary observer. If there is an observer who is just stationary, whatever velocity he will see, that velocity is called the absolute fluid velocity. The word absolute refers to the velocity measured with respect to a fixed observer. The observer is not fixed, he is stationary, he is in the ground, say, and he is observing the fluid that is moving at a velocity of CA. Now there will be a second velocity. Now there will be a blade speed. There will be a blade velocity, which we call it as u vector. This is nothing but the velocity of the blade. The blade itself is a moving component, so its velocity will be u. There will be a third velocity, the relative fluid velocity. We denote it by CR. Now this will be the velocity of the fluid as seen by an observer who is traveling with the blade. If the blade itself is moving with a velocity of u, if there is an observer who is standing on the blade, he will not see the fluid coming at CA, but he will see the fluid coming at some other velocity, which we call it as CR. A stationary observer will see the fluid going in this velocity, whereas a moving observer will see the fluid going in a different velocity. This idea of relative velocity we have already studied in engineering mechanics. So if you are confused with this, you have to go to your engineering mechanics and again recall the ideas of relative velocity. This is a simple idea of relative velocity as studied in mechanics. Now what is meant by relative velocity? It is the velocity of fluid as seen by an observer moving with the along with the blade. If the observer is also moving along with the blade, he is going to see the fluid not in this velocity, but he is going to see in this velocity, in CR. If there is an observer who is sitting on the ground, this is first observer, he will see the fluid going in a velocity of CA. Are you clear? So in any velocity triangles, now this is the study of steam turbines. This is the first place, not the first place. I know you have already done fluid mechanics. You would have seen the velocity triangles for Belton, Kaplan and Francis turbine already. So you already have an idea of velocity triangles. This is the second time that you are studying velocity triangles. So any velocity triangle will have these three velocity components. The absolute fluid velocity vector, the blade velocity will be the second vector, important vector, the relative velocity will be the third important vector. Now what is the relation between them? The relative velocity, this is the definition from mechanics, is the absolute velocity minus the blade velocity from engineering mechanics. Now on rearranging, you just have CA equal to CR plus U. Now in that velocity triangle, these three velocities are there. This is the rule that is obeyed by these three velocities. Are you there? Now let us plot the velocity triangles again for an impulse steam turbine. Now this is the moving blade. This is the moving blade. Now for smooth entry, what should be, which vector should be along the blade angle? If the blade is at this angle, at the inlet, see this is the inlet velocity triangle, this is the outlet velocity triangle. Okay? At the inlet and outlet of the blade, which vector among these three should be aligned to the blade? The relative velocity. The relative fluid velocity should be along the blade. Okay? So this should be CR1 and this should be CR2. Why this is the case? If the relative velocity is not aligned with the blade, then what will happen is, say for example, you have a blade like this. This is the blade angle. The blade direction is like this. If I have a relative velocity like this, okay, say I have a blade velocity like this, okay, then what will happen? It will lead to flow separation. Suppose the fluid relative to the blade is coming like this, or it is coming at some other angle, very much different from the blade angle, then it will not go smoothly into the rotor. While it goes, say, if the fluid comes like this, it will go like this and it creates some separation from the rotor. And this is very bad for a turbo machinery. So in order to have a very smooth flow, attached flow without any flow separation, you should ensure that the relative velocity vector is aligned to the flow direction. Suppose my CR is like this or it is like this, it is different from the blade direction, then it will not hit the blade smoothly. Do you understand? If it hits like this, then it is again going to separate. If it is going to hit like this, again it may lead to separation. So this separation will include a lot of other effects, okay? Because this itself will cause vibration of the blade, and the blade is already moving, it may lead to catastrophe, okay? The blade can even damage because of this effect. It will start from one blade and it will start progressing to other blades also. So to avoid all these complications and shocks, what we do is we have to ensure that the relative velocity vector is nicely aligned to the blade direction. This is some rule that you have to remember whenever you draw a velocity triangle. Along the blade direction, the relative velocity vectors have to be aligned. That is why we call these angles, the angle made by the relative velocity vectors, as the blade angles. You remember? We call the angle made by CR1 and CR2 as beta 1 and beta 2. That's why beta 1 and beta 2 are generally called as inlet and exit blade angles. Why do we call it as blade angle? Because this is the angle of the blade and the relative velocity should be aligned to the blade. So both the relative velocity and blade should be at the same angle. At the inlet, if the blade is at an angle of beta 1, you ensure that the relative velocity is also at beta 1. Suppose relative velocity is away from beta 1, it will lead to flow separation. Similarly, at the exit, if the blade angle is beta 2, CR2 should also be aligned to beta 2. If it is different from beta 2, it may lead to a flow separation. Are you with me? So this is the second rule that you have to remember. The relative velocity vectors should be aligned with the blade directions. Hence, the angle made by the relative velocity vectors are generally referred to as the blade angles. Okay. Now, once you know this idea, you have to use it to complete the relative velocity triangle. The second idea is the blade speed u will along this particular direction. I assume that the blade are moving from horizontally from here to there. So the blade speed is along this particular direction. And wherever the blade is going to move, that direction will be the direction of whirl. Okay. Second principle to note in velocity triangles is along the direction of the blade, that direction is called the direction of whirl. Perpendicular to this direction, this will be the direction of flow. Right? That's why you have inlet and outlet. The flow takes place from inlet to outlet. So actually the fluid is whirling in this direction and it is flowing in this particular direction. So there are two important directions in this velocity triangle. This is the direction of whirl, and I use the letter W for denoting whirl. This is the direction of flow from inlet to outlet. So this is the direction of flow, and I use the symbol F to denote the direction of flow. So this is the second idea. You have to find out these two directions. How to find out the directions? The blade speed will always be in the direction of whirl. The perpendicular direction will be the direction of flow. Now as a last principle, erase this and again redraw. Now as a last principle, let us draw the velocity triangle now. Now you know this is u, the blade speed. You know CR1 has to be aligned to the blade angle. So this is CR1. CR2 has to be aligned again to the blade angle at the exit. So this is CR2. Now you know this is the blade speed. So if this is CR1, this is U1. I just take this vector and I put here. U1 and U2 are same, both are blade speed. Again I take this vector and I put it here. U. Now if I add these two vectors, what should I get? I should get CA1. Are you with me? Again, if I add these two, the vector that I will be getting is CA1. CA2. CR2 plus U2 will give you CA2. Here, U plus CR will give me CA. Remember this rule? If I add CR and U, I have to get CA. Are you with me? Now, this will complete the velocity triangle. This is how I draw the velocity triangles. And then you remember how the angles are made. CR1 makes an angle of beta 1 with the world direction. CR2 makes an angle of beta 2 with the world direction. CA1 makes an angle alpha 1 with the world direction. CA2 makes an angle alpha 2 with the world direction. Are you there? Now, as a last step, we are going to resolve CA1 and CA2. Now, CA1 is like this. This is CA1. I am going to resolve this as CW1. That is the velocity of whirl. This is nothing but the horizontal component of CA1. So if this is alpha 1, then the horizontal component of CA1 will be CA1 cos alpha 1. That I call it as the whirl velocity. And this component, the perpendicular component, I call it as CF1. This is called the velocity of flow. So this is called the velocity of whirl. And this is called the velocity of flow. The whirl velocity and flow velocity are nothing but the components of the absolute inlet velocity. Absolute velocity. Are you with me? Similarly, for the exit, you have CA2 like this. Again, you can resolve it into a horizontal component and a vertical component. The horizontal component will be CF2. The horizontal component will be CW2. The vertical component will be CF2. So this is the flow direction. This is the whirl direction. Now this angle we took it as alpha 2. So CA2 cos alpha 2 will be CW2. CA2 sin alpha 2 will be CF2. Are you there? Now we are going, see, CA1 is the vector. There are only three vectors: CA, U and CR. The components of CA, we are going to give a special name to that: CW and CF. Are you with me? CW is the horizontal component of CA, or the component along the whirl direction. CF is the vertical component of CA, or it is the component along the flow direction. That's why this is called the velocity of whirl. This is called the velocity of flow. We always resolve CA. Okay, we don't resolve CR. So now some books show the these two components also in the velocity triangle. So finally, when I draw the velocity triangle, I will be showing all these components also. Don't get confused. These CW1 and CF1 are nothing but the components of CA1. Are you with me? Now if I show these in this velocity triangle, this is CA1. So its components are going to be like this. Correct? This will be CW1. This will be CF1. Correct? This is CA2. So if I resolve it, this will be CF2. This will be CW. Another thing to note is CW1 is along this direction, right? CA is like this, so its horizontal component is along that direction. Whereas CA2 is like this, so its horizontal component CW2 is along this direction. So remember, CW1 is like this, whereas CW2 is like that. They are in opposite directions. Just remember that. Okay, if they are in same direction, you have something else. They are in opposite direction, it's going to be something else. There is a change in CW1 from CW2. This change is going to give rise to a torque on that particular blade. Essentially, the change in CW is going to create a torque on the blade, and that's what is causing the blade to move in that particular direction. Hence, this change in CW1 from CW1 to CW2 will directly show in the expressions for power, torque, and so on. Now, what we will do is we will sketch the velocity triangles separately once for all and use that for our problems. Okay.